Today we find out what happens when we divide the successive primes of 10 by 13. We are folding arrays, we are receiving bytes of data and swapping them, we are validating credit card numbers, and then we are converting 32-bit unsigned integers into IP addresses. Hello world, and this is Versus Codewars. We begin today with the warm-up segment, a series of easier katas in order to prepare for the more difficult katas later in the episode. Starting with an array and a value, A and X respectively. The goal of this one is to check whether the provided array contains that value. We return true if it does, and false if not. Our function signature is going to look like this. Constant check. We're going to have our array, and we're going to have our X here. And it's very easy to check to see whether this array includes X. What we do is we run the array through the includes method, and we pass in X here. This will return true if X is included in the array. Let's go ahead and punch this into Codewars and see what that looks like here. And we are good on that. Our next warm-up kata. We are lost without a map. Given an array of integers, the goal of this one is to return a new array with each value doubled. Now, we're going to try multiple ways of implementing this particular kata solution. First, we'll do const maps, and we'll have our array here. Our first method of implementing this will be to use the filter method. Array.filter, and our predicate function here, or rather, the array.map method, excuse me. In our predicate function here, we have our element here, passed in, and then we return element times 2. This will create a new array with each of the values in the array passed in doubled. Now, there are more ways to do this than just this, and given the kata here is called lost without a map, let's try doing this without using the map method. Alright, we'll have our function body here. We'll keep track of our result array here, and that is what will be returned. And what we'll do here is, for const element of array, this particular for loop will loop through every element of the array that we pass in, assigning each element to this constant element per iteration. Alright, what we'll go ahead and do is, we're going to do result.push, and we're going to do element times 2. Assuming, of course, all of the elements in this array are numbers. Alright, let's go ahead and pass this into Codewars here and see what this looks like here. And we are good on that. Our next warm-up kata, we are given an array of exactly 3 elements, known as a triplet here. The goal of this kata is to find the numerical element that lies in between the other 2 elements in ascending order of this array here. For example, we have 2, 3, 1. As you can see, the middle number of those is 2, which lies at element 0 here. Let's give this one a try here. And we have our array here, and what we will do with that is we're going to go ahead and run this through the sort method. This, by default, if I'm not mistaken, will sort the numeric elements of this array in ascending order. And what we'll go ahead and do is we're going to go ahead and get the middle element of the resulting array. And I think we just pass in at element 1 here. Let's go ahead and give this a try in Codewars here. And what's going on here? Finds the middle, next to the middle element, expected 2 to equal. Oh, we need the index here. Okay, yep. Probably won't be that simple. Okay. Alright, what we'll go ahead and do is return array.index of array.sort at index 1. So what we'll actually go ahead and do here is we're going to sort this array in ascending order by running it through the sort method. We'll take the resulting array and get to the element at index 1. We'll take that and look for that particular number's index in the unsorted array that we pass in. Let's give this a try here.
Attempt. Find the index of the middle element. Let's go ahead and cancel that long array and see what we're looking at here. We have 2, 3, and 1. Okay. Obviously 2 is the middlemost element here. Alright, let's sort this array here and see what's going on here. We have 1, 2, and 3. Finds the index of the middle element expected 1 to equal 0. Alright, let's go ahead and pass in 1 here. Okay, let's go ahead and do array.index of array.sort. I'm passing in 1.
Oh, okay. So it looks like sort actually mutates the array. So what we actually need to go ahead and do is... Alright, we need a new method of implementing this Kata solution here. So what we're going to go ahead and do is we're going to keep track of a middle value. I'm going to set that... We're going to keep track of a middle value here. Set that to -1. And then for const element of array, if no. Okay, what we're going to go ahead and do is... Alright, let's have a look at the instructions here. As part of this kata, you need to create a function that, when provided with a triplet, returns the index of the numerical element that lies between the other two elements. Okay, Alright, I have a new idea. Alright, what we'll go ahead and do is... We're going to run this through the filter method here. Alright, I have a new idea here. What we're going to go ahead and do... Alright, we're going to go ahead and iterate through each element of our array. We're going to go ahead and get the maximum and minimum values of the elements of our triplet here. Math.max array const min value equals math.min array. And what we'll go ahead and do is, if element is not equal to max value and element is not equal to min value, then we'll go ahead and return our element here. Let's give this one a try here. Still problems, because we need the index of that element. And we are good on that. Our next warm-up kata, we are completing a function so that it returns a URL with anything after the anchor removed. The anchor in this case being a £. Let's go ahead and give this one a try here. Let's remove URL anchor. And we are given a URL as an argument here, URL. And what we will go ahead and do, I think we'll go ahead and try using the slice method here. So what we'll go ahead and do, URL.slice, and we need to slice out starting from the index of our £. Alright, URL dot... Alright, what we'll go ahead and do, URL.index of £. Alright, let's go ahead and feed this into Codewars and see what that looks like. And what's going on here. Oh, yeah, okay. We'll go ahead and start from 0 here and go all the way to that. Oh, okay. Alright, what we actually need to do is, first we need to find the index of our pound sign here. Const index of pound equals URL dot index of our pound sign here. And if index of pound, and we return if index of pound is not equal to -1, then we return URL.slice from 0 to index of pound. And this actually is supposed to be a question mark in our ternary operation here. Otherwise, we just go ahead and return our URL. Alright, let's try this one out here. And we are good on that. Finally, we are checking to see if the numbers in an array are in order. Alright, let's go ahead and give this one a try here. Const in ascending order. Let me pass in our array here. And what we will go ahead and do is let's try running this array through the every method. And then this predicate function will return true if we are not at the end of the array and the value of the next element of the array is equal or greater than this one. Let's go ahead and do element is less than or equal to. We will need the array here. The element of the array at index plus 1. Yeah, either that or index is equal to the length of the array minus 1, indicating that we are at the end of the array. So let's explain what's going on here. We run the array we pass in through the every method, which returns true if every call of its predicate function on every element of the array returns true. In this predicate function, we have our current element, the index of that element, and the array being worked on. We return true if one of the following is true. The current index is equal to the length of the array minus 1, which indicates that we are at the end of the array. Or, the current element being worked on is less than or equal to the element at the next index in the array. Alright, let's go ahead and copy this into Codewars here and see what that looks like. Let's run the tests. And we are good on that. That concludes today's warm-up segment. I will see you in the next kata. The rule of divisibility by 13 is as follows. Division of the successive powers of 10 by 13 will result in the following sequence of repeating remainders: 1, 10, 9, 12, 3, and 4. Given an integer n, the goal of this kata is to multiply the rightmost digit of n with the leftmost number in the aforementioned sequence, and then multiply the second rightmost digit of n with the second leftmost number in the sequence, and so on. The products are then added together. This process is repeated upon each resulting sum until a stationary sum is reached, in which repeating the process on that sum will result in the same exact sum. Let's go ahead and give this a try here. Alright, what we're going to go ahead and do, we're going to keep track of a current sum, or rather a previous sum, we're going to set that to, let's say, number. All right, we're going to go ahead and do a while loop here, while true. And what we'll go ahead and do, actually, we do need to keep track of a current sum. And what we'll go ahead and do is we're going to go ahead and take that current sum and get the digits out of it. Current sum, we're going to go ahead and convert that into a string, split that into its individual characters, and then map each individual character into an integer using parse int upon that character. Alright, next what we need to go ahead and do, we need to generate a sequence of that sequence of numbers that we just talked about up to the length of the digits array. And what we'll go ahead and do is const remainders equals, we're going to take our digits array and we're going to run that through the map method. In this predicate function, we won't be using the digit itself, but rather the index. And what we'll do is we're going to use the math.pow method, and we're going to raise the number 10 to the power of the current index of the digits array. We're going to take that resulting exponent and divide that by 13 and get its remainder. Alright, what we will go ahead and do from here, we want to calculate a new sum here. Constant new sum. And what we will do is we're going to take the digits array and reverse it. That way we're getting the rightmost digit of n. So what we'll do is digits.reverse. We're going to take that resulting array and run it through the reduce method. Now, in its predicate function here, we're going to need the three of the arguments here: an accumulator, the current digit, and the index of that digit in the digits array. And what we'll go ahead and do is we're going to return the accumulator and we're going to add together the current digit times the index the element in the remainders array at the given index here. Remainders at index. So let's explain what's going on here. All right, we take our digits array, we reverse it, and then we run that reversed array through the reduce method here. And its predicate function here, we have three arguments: the current accumulator, which will initially be set to 0, the current digit we are working on in our digits array, and then we also need the index of that digit, because we will be pulling the remainder from the remainders array at that particular index. It's safe to assume that digits and remainders will have the same number of elements, so there should be no problems there. What we do here, we take the accumulator, which is initially set to 0, and we add together the product of digit times the remainder in the remainders array at the given index here. And as a result, we should have our new sum. Now, what we need to do is we need to check to see if that new sum and the current sum are the same number, in which case we would have a stationary sum. So we take new sum. If new sum is equal to current sum, then we return new sum. Otherwise, we take our current sum and set it to new sum for the next iteration of our while loop here. All right, let's go ahead. Let's explain what's going on here. Here we have our Kata solution. When we pass in our number here, we set that number in as our current sum here initially. Now, in our while loop, we take that current sum and we get the digits out of it by converting it into a string, splitting it into its individual characters, and then running that resulting array through the map method, parsing each character as an integer. Next, we get the remainders of our divisibility by 13 sequence. And we do that by taking each digit and running it through the map method here. We don't use the element itself in the predicate function, but rather the index. And what we do is we use the math.pow method to raise 10 to the power of that index. And then we take that and divide it by 13 and get its remainder. Next, we calculate the new sum that we will be working with in the next iteration of the while loop here by taking the digits, reversing them, and then running that resulting array through the reduce method. In its predicate function, we have the accumulator initially set to 0, the current digit being worked on, and the index of that digit. Now, we take the accumulator and add together the digit multiplied by the remainder in the remainders array at the given index here. Now that we have our new sum here, we compare it to the current sum, and if they are equal, then we know we have a stationary sum, and that is what will be returned from the Kata function here. Otherwise, we set the current sum to the new sum for the next iteration of the while loop. Let's go ahead and test this out here. Alright, we have a console.log down here with a call to our Kata function here, passing in 1,234,567. Let's go ahead and test this out here. Node divide by 13, and we get 87, which is the stationary sum that we were expecting here. Let's try another number here, 321. And we get 48, because 48 is the stationary sum. Let's try some larger numbers here. 987654321. And let's try saving that first. And we get 30. How about this extravagantly large number here? What is that? 1,111,111,111. And we get 71. Alright, let's go ahead and punch this into Codewars and see what this looks like here. Let's run the tests. And we are good. Here's another way to implement this Kata solution using recursion rather than while loops. Pay mind to the code snippet you see below me here. Now, since we already know what the numbers are going to be in our divisibility by 13 sequence, we can just go ahead and hard code those numbers into an array, rather than programmatically calculate them as we did in our Kata solution here. Alright, we can take our number and we convert it into a string, albeit in a different way than what we did in our Kata solution. We split it into its individual characters to get its digits. However, we skip the map method here because we know that if we run strings through arithmetic operations, JavaScript will attempt to implicitly convert those strings into numbers. Now, in our our reduce method here, we reverse the digits here, and then we run that through the reduce method here. We have our accumulator, our value, and our index, as we had in our Kata solution. We take the accumulator, which is initially set to 0, and then we add together the product of the value times the element in our remainders array at the index I modulo remainders.length here. Now, we do that to avoid going out of bounds in the remainders array here. Now that we have our sum, we check to see if that sum is equal to the number that we passed in which case we return that number. Otherwise, this is where the recursion comes into play here. We return the return value of another call to our Kata solution function, passing in the sum. This will recurse and repeat itself until we get our stationary sum. Given an array of integers, the goal of this Kata is to fold that array such that the element x indices to the right of the center is added to the element x indices to the left of the center of that array. This process is repeated a certain number of times here. Let's go ahead and get started with this one here. We have our function here called fold array. It takes our array of integers and the number of times we have to fold that array. Let's go ahead and give this a try here. Alright, let's handle some edge cases here. Now, if the array is only one element in length, we'll just go ahead and return that array. Alright, what we'll go ahead and do is, I think we're going to go ahead and, alright, we need to figure out how many elements there are in the array, and if, what we can go ahead and do is half array. Figure out 1/2 of the array's length. Half length. And what we'll do is math.floor array.length divided by 2 here. Alright, and what we'll go ahead and do for let I equals 0, I is less than half length plus I. Alright, what we'll go ahead and try doing here, let's actually go ahead and get the reverse of that array as well here. Const array reversed equals array.reverse. Alright, what we'll go ahead and do is, I have an idea. I actually don't need to reverse that. What we can go ahead and do is, we're going to go ahead and slice that, make a copy of this array and slice it. That way we don't manipulate this original array here. And then what we'll go ahead and do is array sliced at index I plus equals array sliced dot pop. And then what we can go ahead and do with that resulting array, we're going to run a little bit of recursion here. We're going to turn fold array. We're going to take that, pass in the array sliced, and then we're going to pass in times -1. Alright, so let's explain what's going on here. Here we have our fold array function, and it takes 2 parameters. Our array of integers and the number of times the array needs to be folded. Now, at the start here, we have a couple of checks here. We need to check to see if the length of the array is greater than 1 and the times is greater than 0. Now, if this array has only 1 element in it, or we passed in 0 to the times here, we just go ahead and return the array. Otherwise, what we'll go ahead and do, in order to prevent manipulating the original array, we make a copy of the array using the array objects, slice method, passing in nothing in order to make a copy of all the elements of the array here. Next, we go ahead and calculate an approximate half length of the array. And what we go ahead and do, we take the length of the array and divide it by 2, and then we run that quotient through the math.floor function to round that down to the next integer. Now we go ahead and loop from 0 to that half length. Alright, we grab the integer of the array sliced at index I, and then we add to that the return value of the array sliced.pop method, which pops the last element of that array out. So as a result, we should have this array folded here. Alright, we go ahead and repeat that by doing a little bit of recursion, returning the return value of fold array, passing in our array sliced, and our number of times minus 1. Alright, let's go ahead and give this a test run here. Alright, I'm going to go ahead and do this one here. Console.log. Old array. We're going to pass in 1, 2, 3, 4, 5, and we're going to pass in 1 for the number of times. Let's feed this into Node and see what that looks like here. And we have an array 6, 6, and 3, which is what we want to see. Let's pass in 2 for the number of times here. And we get the array 9, 6, which is what we want to see. Let's have a look at some of these tests here. How about this one here? How about this array here? Minus 9, 9, minus 8, 8, 66, and 23. Now I expect to see the array 14, 75, and 0. Do we see it? Yes, we do. Alright, let's go ahead and feed this into Codewars and see what that looks like. And we are good. The trick to this Kata solution is as follows. We want to make sure that the centermost element of the array is never touched if we're dealing with an array with an odd number of elements in it. What we do is we take the length of the array and divide it by 2, but then we use the math.floor function to floor that quotient, to round that quotient down to the next integer. That way, when we loop through from 0 to that half length here, we make sure that that centermost element is never touched. This is not an issue if the array's length is an even number. Given an array of 1s and 0s representing binary bits in a stream of data that's just been received, the goal of this kata is to take each 8 bits at a time, each 8 bits representing a byte, and reverses them. For instance, the binary bit sequence 1111000000001111 is reversed to become 00011111110000. Alright, let's go ahead and give this a try here. Alright, what I think we'll go ahead and do, I want to try grouping each of these bits into bytes here. So what we're going to go ahead and do, counts bytes, we're going to set this to an empty array here. And I think for let I equals 0, I is less than data.length. I is plus equals 8. So we're starting at 0, looping to the length of our data array here. But instead of plus plus I, we're stepping our I up by 8 with each iteration here. So what we're going to go ahead and do, we're going to try this. Bytes.push data.slice I to 8. Alright, let's go ahead and console.log that and see what that looks like here. I'm going to do this console.log data reverse. We're going to go into our Kata instructions here and pass in our array here. This array here. So we got this call to data reverse, and we have this array of binary bits that we pulled from the Kata instructions here. Let's feed this in a node and see what this looks like thus far. Node data reverse. And that's not what we wanted. Okay. Alright. Where are we going wrong here? Alright, we're starting I0. Right. Slice wants an endpoint, not how much we're slicing. Let's try that again here. We have our 1 1 1 1 1 1 1 1 here for the first set of bits. straight zeros for the second one, 4 zeros, 4 ones for the third, and then alternating ones and zeros for the fourth here. Alright, what we should be able to go ahead and do from here is... Alright, what we're going to go ahead and do is return bytes.reverse. And then we're going to run that resulting array of arrays through the reduce method here. Actually, no, I can't quite do that here. Alright, I have an idea here. Alright, I have an idea here. We'll go ahead and do return bytes.reverse.reduce. We'll have an accumulator and our byte here. And what we'll go ahead and do is we'll return, spread out our accumulator here. And then we spread out our byte here. And we set the initial accumulator to an empty array. Let's go ahead and see. This looks like punch this into node here. And we do in fact see our bytes have been reversed here. Alright, let's explain what's going on here. Here we have our function data reverse, and we take our array of binary bits right here. Now, we keep track of our reversed bytes right here. Now, in our for loop here, we in loop I from 0 to the length of the array that is passed in here. However, instead of ++i, we instead step up I by 8 at the end of each iteration here. Now, in each iteration of our for loop here, we push in a new array to our bytes array here. And this array will be our data array sliced from I to I plus 8. In other words, we take the next 8 bits in our data array and we push that in as a new array into our bytes array right here. Now, we take that resulting array of arrays of bits. We reverse it, and then we run that resulting array through the reduce method. We have our accumulator here, which is initially set to an empty array here, and the array of bits making up our byte here. Now, in the body of this predicate function here, we spread out, using the spread syntax, the bits that we already have in our accumulator array here. And then we spread out the bytes in our new byte right here. And then we return that resulting array, and that will be the new accumulator here. Now, the resulting array should be our bytes that were passed in, reversed by the byte, by each 8 bits here, as we see in our result right here. Let's go ahead and punch this into Codewars and see what that looks like here. Let's run the tests. And we are good. Here is the better code solution of the day. Pay mind to the code snippet you see below me here. As we do in our Kata solution, we loop from 0 to the length of our data array, stepping up by 8 each iteration here. However, what this Kata solution does is take advantage of the fact that you can pass in more than one argument into the array object's push, or in this case, the unshift method. Those 8 arguments in question here are the resulting array returned from data.slice, slicing from I to I plus 8, spread out into the 8 arguments passed into this particular call to unshift. The result is each of the bytes of the array passed in reversed to the correct array that is returned from this Kata solution here. This is a common practice in network programming here. Each of most all computers nowadays run in little endian mode, in which the least significant byte is stored at the smallest memory address. However, what is known as the network byte order is big endian, in which the most significant byte is stored at the smallest index, thus necessitating the need for swapping bytes when we're sending data over the network or receiving data over the network. The Luhn algorithm is used to validate credit card numbers and works as follows. Step 1. Double every other digit starting with either the first or second, depending on whether there are an even or odd number of digits passed in. Step 2. Subtract 9 from each double digit greater than 9. Step 3. Add together all of the digits. And in step 4, divide the sum by 10. If the remainder is 0, then the credit card number is valid. Given a positive integer n, up to 16 digits in length, the goal of this kata is to apply the Luhn algorithm in order to check to see if that integer is a valid credit card number. Alright, let's go ahead and give this a try here. Alright, first we need to check to see if... First we need to split this number into its individual digits here. n.toString, split. Now, we need to check to see if there are an even number of digits here. Is even digits. We'll go ahead and do digits modulo 2 is equal to 0. Check to see if we're dealing with an even or odd number of digits here. Alright, what we will go ahead and do is... I think we'll go ahead and try using the reduce method here. Const sum equals const Luhn sum equals digits.reduce. We have our accumulator and our value and our index here. Set our initial accumulator to 0 here. Alright, what we'll go ahead and try doing here is alright, if we're dealing with an even number of digits here, then what we need to go ahead and do is we're gonna double starting from the first digit here. Alright, return. Alright. Yeah, if even digits is true here is value time. Okay. If even digits is true and index modulo 2 is equal to 0, then what we'll go ahead and do is value equals value times 2 times equals 2. And we'll do the same if is even digits is false and index modulo 2 is not equal to 0. Now, if the result of that is greater than 9, we need to subtract 9 from that. And then we'll go ahead and take that resulting value and add it to the accumulator. Alright, what we'll go ahead and do is... I'm going to have a look at the Kata instructions here. So I'll go ahead and console.log that Luhn sum here. We're going to go ahead and test that out here. Console.log validates pass in 891 for this one here. Let's feed this in a node and see what that looks like here. 08181. Huh, that is not what we're looking for here. That could well be because we're dealing with strings here. Alright, let's go ahead and console.log the value here. Ew, okay. Alright, what we're gonna go ahead and do up here, we're gonna go ahead and .map convert these into integers here. Alright, we're gonna go ahead and console.log our value here. 818.1. Value minus equals 9. There. And we get our 891, we get our 18. Alright. From here, what we can go ahead and do, we'll return true if Luhn sum we take Luhn sum divided by 10, get the remainder, and if it's 0, then we know it's a valid credit card number. If it's not, we go ahead and return false. Alright, let's go ahead and try that again. That should give us false, because it's not a valid credit card number. Okay, let's try some other tests here. 1230 should give us true, but it's giving us false instead. What's going on? Console.log value. One, 4, 3, 0. Yeah, even number of digits here. Okay, that's not right here. Alright, what's going on here? Let's go ahead and console.log our digits here. We have our 1, 2, 3, and 0 here. Digits.length. Okay, that's correct here. Problem was, we were attempting to divide the digits array by 2. That was never going to work. We needed to use .length here. Alright. Let's try some other tests. How about 1, 2, 3? Which should give us false. About 1. Just a 1. That gives us false. Let's try 21, 21. Should give us true. Okay. Let's explain what's going on here. We have our validate function here, which takes n, our integer, as a parameter here. We take n here and we split it into its individual digits, just like we have done in the previous katas here, converting it into a string, splitting it into characters, and then parsing int out of those characters here. Alright, we need to check to see if this resulting array has an even number of elements. Rather, this integer has an even number of digits, whether it's even or odd. And we do that by taking the length of this digits array and dividing by 2 and getting the remainder. If it's 0, then this is even. Otherwise, this is odd. Next, we calculate what we call the Luhn sum of those digits here. We take the digits and run it through the reduce method here. We have our accumulator initially set to 0, our current value, and our index. First, we check to see if we need to double this value here, and we will do so if one of the following conditions is true. A, this digits array has an even number of elements, and B, A, the digits array has an even number of elements and the current index is an even number. Or B, this digits array has an odd number of elements and the current index is odd. In either of those cases, we double the value here. Now, if doubling the value causes the value to be greater than 9, we go ahead and subtract 9 from that value here. We then add the manipulated value to our accumulator here to produce our Luhn sum right here. Finally, we go ahead and divide that Luhn sum by 10 and check the remainder. If that remainder is 0, then the number we passed in is a valid credit card number. Otherwise, it is not. Alright, let's go ahead and feed this into Codewars and see what that looks like here. And we are good. Not really much to say about this one. However, I could have gotten rid of some repetitive code in my reduce method's predicate function here. I could have just used a single if statement, checking to see whether the evaluation of index modulo 2 is equal to 0, evaluated to the same Boolean value as the Boolean value of our is-even digits variable. Consider the following IPv4 address, 128.32.10.1. This address has 4 octets, where each octet is a single byte, or 8 bits. The first octet is 128, and has the binary representation 10000000. The second octet is 32, and has the binary representation 00100000. The third octet is 10 and has the binary representation 00001010, and the fourth octet, 1, has the binary representation 00000001. Alright, because that above IP address has 32 bits, we can represent it as an unsigned 32-bit integer. I believe that is 2,149,583,361. Given the integer form of an IPv4 address, the goal of this kata is to return the string representation of that IPv4 address. Alright, let's go ahead and give this a try here. Now, we know this integer has 32 bits to it. I think we can try using the bitwise shifting operator here. What we can go ahead and do, we're going to go ahead and console.log this into 32 that we passed in here. And we're going to go ahead and pass this in here. Console.log into 32 to IP. We're going to pass this in. Speed this in a node and see what that looks like. Int 32. And we have that integer form right here. Let's go ahead and console.log that same int 32 shifted right by 24 bits. And we have 128. Let's try coercing that to an unsigned int. And we have 128 here. Now, how about, what if we tried going ahead and console.logging our int32 shifted right by 16 bits? What would happen here? We get 32,800, and that's something we actually do not want. So what we'll go ahead and try doing here, we'll encapsulate this in parentheses, and we'll use the bitwise AND operator. And we'll AND that by 0 times FF, or 255. And we get our 32. And so far, so good. We can repeat this for like the other 3 octets of our IP address. 8, and then 0. And we get our 4 octets. 128, 32, 10, and 1. Alright, let's go ahead and comment this out right here. And we'll put this to practice here. What we'll go ahead and do, we're going to set up a little bit of an array here. What we'll do is return the following array. What we'll do, int32, Int32 shifted right by 24 and OXFF. Int32 shifted right by 16 bits and OXFF. Int32 shifted right by 8 bits and OXFF. And Int32 XO and OXFF. And we will join this together using a period separator. Let's run this through Node and see what that looks like. And we have our IP address here, 128.32.10.1. Let's go ahead and get rid of these comments here in the console.log. So, what's going on here? We're doing a little bitwise mathematics right here. Alright, for each of our octets here, let's start with our first octet here, our int32. This is the coerced, the unsigned right shift bitwise operator right here. What this does is takes this integer and in this case shifts it to the right by 24 bits. Now this particular operator coerces the result into an unsigned integer. So this is guaranteed to be a positive here. What we do after that is we use the bitwise AND operator to AND it with the integer 255, 0xff. Now the bitwise AND operator, I'll give you an example here. We have 0 and 1. If we run these two through the bitwise AND operator, we should expect to get 0 here because 0 is not 1. So, yeah. And the other, so this next one here, we shift this very same integer right 16 bits and AND that by 0xff to get our second octet. We repeat this 2 more times to get the other two, the last 2 octets right here. Here in this case, we don't shift this at all. Alright, let's go ahead. I hope I explained this well enough here. Let's go ahead and punch this into Codewars and see what this looks like here. Let's test it out here. And we are good. Shown in this Kata solution are a couple of instances of bitwise operations. First is the unsigned right shift bitwise operator. You may have seen me try using this on an earlier episode of Versus Codewars when I was attempting binary addition. This operation takes the integer on the left-hand side and shifts its bits rightward by the number on the right-hand side. Now, what this operator does additionally is coerce the result to be an unsigned integer, so it's never negative. The other piece of bitwise operations I used here is the bitwise AND operator. This takes the corresponding bits of the left-hand and right-hand integers and compares them. Let's do a little bit of an example here. Consider the decimals 5 and 3. The binary representation of 5 is 0101, whereas the binary representation of 3 is 0011. Let's compare the corresponding bits here. First, 0 and 0. They AND out to 0. Next is 1 and 0. Because 1 is not 0, 1 and 0 AND out to 0. Next up is 0 and 1. 0 and 1 are not the same, so that also ANDs out to 0. And then finally, we have 1 and 1. Since they are both 1, these two AND out to 1, resulting in our solution here, which is the decimal 1. And that will do it for today's episode of Versus Codewars. If you like this video or you learned something new, drop a like and subscribe to my channel to see me take on more coding challenges on Codewars. As always, if you think there's anything I can do to improve on my code for the better, feel free to drop a suggestion in the comments section below. I hope you have a wonderful day, and I will see you on the next episode of Versus Codewars.